This is assignment 16, question 5.84 from the Silverberg textbook. In this case here, you have a balloonist who starts out the morning in a helium-filled balloon. Helium is monatomic. There's our CV and CP. Starts out at 15 degrees Celsius. And by midday or mid-afternoon, our temperature is up to 30 degrees Celsius. The pressure remains the same at 1.01 bar. And so I've just switched these into kelvins and atmospheres. And they want to know the following variables here, the following answers per mole of helium. So that's why I'm putting N as 1 mole. So we'll start out with initial and final volumes. So you can easily get these. This is an ideal gas. So V1 is going to be equal to nRT over P. In this case here, pressure is constant, nR constant. I have that initial temperature. Just watch your units. So in this case here, if you are using atmospheres down here, you're going to be using the liter atmosphere, so little r, 0.08206 liter atmospheres. So you're going to end up with a value of 23.6 liters. You can do the same thing for V2 using T2, and you should end up with 24.9 liters. So we're getting an expansion of this helium-filled balloon. You could have also switched your pressure into pascals. So if you're in pascals here, this pascals, you're going to be using big R, so 8.314, and your units of volume are going to be meters cubed. Now, next thing, we're going to go for, we can do either delta U, we can do work. Do we have everything we need for delta U? So, well, it is what they're asking for next. That is B. The delta U, expansion or compression of ideal gas, is NCV delta T. I know N, I know CV, and I do have delta T because I have the two temperatures. So working this out, this is now going to be 3/2 nR delta T, where R in this case here, remember I want a unit of joules. So R I can put as 8.314 joules per mole Kelvin. So I only end up with joules in the end. So delta U, you should have an answer of 187 joules. Remember that's T2 minus T1, so you have a 15-degree difference. Now C is the work. The work is equal to negative P external delta V. This is where you have to watch your units again. I know I've said this in a couple of the questions that have gone over in these little sessions. If you're going to use atmospheres and liters, just be prepared to convert that into joules. So in this case here, if I do use that, I use my atmospheres, 1 atmosphere, and my liters here, V2 minus V1, you're going to end up with a value of minus 1.3 liter atmospheres that you then have to transform into joules by multiplying by, I'm just going to add it on here, 101.325. That's joules per liter atmosphere. So your work is going to be minus 132 joules. Now we can move on to our heat, so part D. So it's pretty simple because I know delta U and I know work. So D, heat equals delta U minus work. We know both of those, so you should end up with a value of 319 joules in this case. Now, E, delta H. So our general equation for delta H, expansion or compression of ideal gases, NCP delta T. That's going to be N, or sorry, 5/2 nR delta T, which we have all of that. And if you work this out, you end up with 312 joules, which is extremely close to our heat that we calculated, 319, almost identical because it depends on how many units you've kept and what conversions you've added, or how many decimals you've kept. These guys are pretty much identical. So part F is asking you to comment on the similarities here. Now, if you think back to what type of process this is, you're told that the pressure is remaining constant. So this is a constant pressure process. Heat at constant pressure is delta H. So they should be the same. And if you think a little further here, your definition for enthalpy is delta U plus P delta V, or delta PV, but P is a constant in this case, so it's being pulled out. This is rather familiar. In this case here, our external and internal are the same, right? It's just maintaining that pressure. So this is really work. If you were to write all this out then, so delta U is Q plus work, and this is our minus work. So our delta H should equal our heat at constant pressure.